So thanks a lot for the invitation. It's my pleasure to speak here. So all right. So my title is already on the screen. And I should say a lot of this is based on a joint work with Chenyang Xu. Okay. So let me first tell you where the problem comes from. So basically, if you start with the a sequence of K-Einstein Fano manifolds. So let's say I have a K. So these are K-Einstein Fano manifolds. Okay, so K-Einstein just means it's a Kähler metric whose Ricci curvature is constant. Okay, so and Fano means the Ricci curvature is positive. So basically, this means the Ricci. If you rescale the metric, then the Ricci curvature is the same as the metric itself. Okay. And now if you have an infinite sequence of this, it was proven by Donaldson and Sun before that after passing to a subsequence, you can actually extract a Gromov-Hausdorff limit, which is also has some structure of this kind. Okay, so let me state what their result says. So after passing to a subsequence, you can take the limit. Okay, so maybe after passing to subsequence, and you go to the limit, you can get the so-called Gromov-Hausdorff limit. Okay, so let me call this limit space X infinity. So priori it's a metric space, but then Donaldson and Sun show that this X infinity is actually also it's also Fano, okay, but it's no longer smooth. It's only a Fano variety. So the variety part means that it's possibly singular. But the Kähler-Einstein metric also goes to the limit. Okay, so all the structures you see, at least the metric structure you see on the before taking the limit, goes through to the limit, except that you have to allow some singularities. Okay, so that's the upshot of this statement. So then maybe we should understand this singularity. So the second part of their Donaldson-Sun's result says that, all right, so how do I understand these singularities? One thing we can do is to look at the so-called metric tangent cone. So they start to analyze the metric tangent cones of this singularity. So because let's fix a singular point. And because I said it's Kähler-Einstein, so let me also give a name to this Kähler-Einstein metric. Okay, so now so how do you do this? Well, so if you want to zoom in at the singularity and look at the local structure, and one thing you can do is to rescale this metric. So this time you choose some parameter, rescaling parameter that goes to plus infinity. And again, you extract a Gromov-Hausdorff limit of metric spaces with a base point. So I rescale this metric, and let lambda goes to plus infinity. Then locally the space gets flatter and flatter, and in the end, if you extract a pointed Gromov-Hausdorff limit, what you get is the so-called metric tangent cone. Okay, so let me again give a name to this. And again, it comes with this metric which is going to be flat this time because the curvature will decrease to 0. Okay, so in the end, what Donaldson showed in this context is that after going to the limit, this metric part is going to be a Ricci flat Kähler cone. And what might seem a little bit surprising is that this y has some algebraic structure. So this is an affine algebraic variety. Okay, I'm trying to squeeze a lot of things in this small space. Maybe that's bad. But anyway, so this is what they discovered. And because of this, this ubiquities of these algebraic structures throughout this limit procedure, that led Donaldson and Sun to conjecture that, okay, so maybe there should be some algebraic geometric understanding, interpretation of this process. So in particular, one of their conjecture is that, okay, so if, let me fix the setting. So if X, so maybe let's call, so let's say X infinity is the Gromov-Hausdorff limit of this Kähler-Einstein Fano manifolds. Okay. But on the limit, as I said at the beginning, X infinity can be singular. Then the metric tangent cones of any singular point or even a smooth point on this Gromov-Hausdorff limit only depends on the algebraic structure of the variety. And right, so it only depends on the algebraic structure of this variety, and in particular, not on the metric. Omega. Okay, so that's one thing that they conjecture, and if you want to be more ambitious, you might want to even give an algebraic geometric construction of this metric tangent cone if it only depends on the algebraic structure. Because right now, if I want to get this tangent cone, I really need to take this Gromov-Hausdorff limit as metric spaces. Okay, so maybe the next level of question is to give an algebraic geometric interpretation of this metric tangent cone. Okay, so basically this is the question I want to focus in this talk. All right, so now before I move on, let me first tell you what's the actual context I want to work in. So so as a general fact, the singularities on this Gromov-Hausdorff limit of Kähler-Einstein Fano manifolds are special examples of a bigger class of singularities, particularly in birational geometry. So it is known that the singularities of this X infinity, this Gromov-Hausdorff limit, they are so-called Kawamata log terminal. Okay, so I'll usually write this as KLT. So this is a singularity class that comes up in birational geometry. So the definition of being KLT is that, so let's say a singularity is KLT. If first of all, the canonical divisor, okay, so this is Q Cartier. So some multiple becomes a line bundle. And if you look at the log resolution, right? So if you want to understand the singularity, we'd better take some log resolution. Then I can look at the relative canonical divisor, which is the canonical divisor on the top minus the pullback of the canonical on the bottom. Then this is the only difference is concentrated on the exceptional divisors, and I require that the order of vanishing along the exceptional divisor is bigger than -1. So that's the definition. So intuitively, you can do this as saying that the holomorphic forms, if you take the holomorphic forms on the singular space, then the singularities of these holomorphic forms are better than log poles. So that's one way to interpret it. And some examples are so quotient singularities, cons over Fano varieties, and also their deformations, etc. Okay, so it's a pretty big class of singularities. All right, so at the end of the day, what I really want to talk about is a generalization of this metric tangent cone to this bigger class of singularities, and how to construct it without, in particular in this larger context. A priori, I don't think there is the most natural metric we can impose on them. At least I'm not aware of that. So then having an algebraic geometric interpretation would enlarge this homogeneity of this metric tangent cone construction to this more algebraic geometric class of singularities. Okay, so that's our goal. Any questions about this setup so far? Okay, so now let me continue. So basically, I should first say the original Donaldson-Swen's conjecture was known. So this conjecture was proved so I guess in two papers. So one part by jointly with Shili and Chenyang Xu. Okay, so this Shili and Chenyang Xu, and then also by Shili Xiaowei Wang and Chenyang Xu. Okay, but all this works actually goes back to an initial insight of Shili, where he realized that so if you want to give an algebraic geometric interpretation of this metric tangent cone, the key concept comes from the notion of valuations. And this metric tangent cone construction comes from a particular valuation that minimizes the so-called some invariant called the normalized volume. So this goes back to the work of Xu. Okay, so instead I want to set up an algebraic formulation of some variational principle. That's the rough strategy. Okay, so let me define some of these names. So what's a valuation? Well, so a valuation for us, so basically it's assignment of values. You can think of it as a function on the function field of the variety. Okay, so now let's fix x in x. It is a KLT singularity just for simplicity. And then the valuation, let me call it V. So basically for any algebraic rational functions on the variety x, I want to give it a value. Okay, so maybe I should call this a real valuation because it takes real values. And then it has to satisfy. So if I multiply two functions, the values add up. And if I take the values of x plus y, then there's some. So basically, there's some non-Archimedean version of triangle inequality. Okay, so that is a valuation. Maybe some examples to keep in mind is so the first kind of example is so if I take a log resolution of my singularity, and then if I take a prime divisor on the log resolution, then I can look at the order of zeros or poles of a function along this divisor. Okay. So then this is a valuation. And if you want to get real values, you can rescale it. Okay? So I can always multiply it by some real number of the actual number of order of zero, suppose. Okay, so that's the first kind of example. This you recall the divisorial valuation. And another example you can think of is called quasi-monomial valuation. So instead of having one divisor, I take multiple divisors and then look at the intersection of their stratum. So let me write it down. So again, there's some log resolution, but then I choose a bunch of divisors on the resolution. So on the top, there's simple normal crossing. And then along the intersection of this EI, I can assign different weights along different components. So I want to declare that if I evaluate this EI, so the local defining equations of this EI, I get some value, maybe alpha I. And then so for other functions, so you can think of this EI, the defining functions of this EI give you local coordinates. So I assign different weights to these local coordinates. So maybe let me call it xi, yi maybe. Okay, so this E is yi equals 0. And then once you assign weights to these coordinates, you can talk about weighted multiplicities of a rational function, or at least a holomorphic function. Okay, and then extend that as a valuation as well. Okay, so this is a generalization of the divisorial case, which only concerns one component, and this is called a quasi-monomial valuation. Okay, so basically you want to give different weights to different coordinates. That's the idea. So in some sense, this can be so, and I think that's also one of the original idea of Shirley, is that this kind of assignment of values to rational functions is a little bit like an analog of doing rescaling, right? So, but you want to do different rescaling factors in different directions. Okay, so in some sense, that's going to replace the metric analog. Okay, so this valuation is going to be some kind of algebraic rescaling. I mean, rescaling refers to the part that we use for constructing the pointed group of Hausdorff limit. Okay, so, and how do I get a valuation to the limit? Okay, so this is just the first object. Okay, and now how do I get a valuation to the limit? Well, so the idea is to mimic what we are more familiar with in the vector bundle case. So algebraically this where is it? Algebraically, this kind of growth of Hausdorff limit is some kind of isotrivial degeneration. So you want to write down a family depending on the parameter. So here the parameter, for instance, is lambda, such that for general parameter, what we get is the same algebraic variety, but then when the parameter approaches to a certain limit, the algebraic structure jumps. Okay, so this limit procedure that we want to have is some kind of isotrivial degeneration. So if you think about a vector bundle, how do you get an isotrivial degeneration? So one thing you can do is to take a filtration of a vector bundle. So this E is going to be a vector bundle. And then I choose a filtration of subbundles. And then I can use this filtration to degenerate E to the associated graded pieces, the direct sum of associated graded pieces, right? Just by specializing all the extension class to 0, okay? And then it becomes the direct sum. So we want to mimic some kind of So you can get a filtration in this way. Okay, so from a valuation, we can write down a filtration. Where each individual piece in this filtration is going to be an ideal. Depending on this valuation, this you recall the valuation ideals. But they are nothing but the collection of algebraic functions in R such that the values is at least nitrogen index lambda. So this is just defined as a direct sum of all the associated graded pieces. Okay, so I take this valuation ideal and multiply the next one. And I have to sum over all the possible indexes. Okay, so get a graded algebra in this way. And so ideally, associated to this filtration, associated to this valuation, should be the spectrum of this algebra. Okay, so that's roughly the idea, but there are two issues here. So the first one is which valuation we should choose. And another more serious issue is that if I want to take the spectrum and get an algebraic variety, bear in mind that this is what we want to replace for the metric tangent cone. So we're going to think of this as a replacement of the metric tangent cone. And so that's supposed to be an algebraic variety, but there is no a priori reason why this algebra, after we form the associated gradient, should be finitely generated. Okay, so if I want to get an algebraic variety, I'd better have finitely many generators because that's my coordinate functions. So that's another issue we need to solve. Okay, so but at least ideally this would be the strategy. So let me first talk about how should we pick the valuation. And this is related to this normalized volume that Shirley introduced. So I'll try to be brief about this definition. So it combines two more classical invariant in algebraic geometry. So if you have a valuation and a KLT singularity, and then V is a valuation. There are two invariants you can define. So the first one is called the log discrepancy. Which so if you do it for divisorial valuations, okay, so let me do it this way. So basically it's determined by three properties. So first of all, if you rescale the valuation, it also rescales. So it's linear. And then if you evaluate it on divisorial valuations, what you get is the order of poles for that relative canonical divisor. Okay, so if y to x is this log resolution plus 1. Okay, so and because the variety is KLT, as I said before, the holomorphic form says that was log poles, so this is positive. It's better than log poles, so this is positive. And then for general valuations, you have to do it by approximation. So let me define by divisorial valuation, by approximation using divisorial valuation. Okay, so let me try not to write that down. Okay, so that's the first part of the classical invariant that goes into this normalized volume definition. And there is also something called the volume of a valuation, which basically measures the growth rate of the co-length of this valuation ideals. So these valuation ideals, they are decreasing as lambda increases. And if you look at the length of this quotient, it's going to grow like lambda to the dimension. Okay, so let's call n the dimension of this x. Okay. Then if you take the limit, maybe at least the lim sup, what you get is called the volume of this valuation. Okay, so you can imagine if you have a smooth point and this valuation is just the multiplicity. Sorry, maybe if you have a general singularity and this v is the ordinary, comes from the ordinary block of that singular point, then what you get here as the volume is exactly the multiplicity of the singularity. Okay, so this is some Hilbert-Samuel polynomial type of thing. Okay, so now this volume also changes when you rescale the valuation. So if I change the valuation v to lambda times v, then this becomes lambda to the minus n times volume of v. Okay, so and then Shirley's idea is to combine these two and get an invariant that's rescaling, invariant under rescaling. So this normalized volume defined by Shirley is the following. So he calls it volume hat. So the normalized volume of my valuation v is just, okay, so it's basically the only way to combine these two invariant, the log discrepancy and the volume, so that the resulting number is does not change under rescaling. Okay, so if I take the log discrepancy to the n times the volume, then all this rescaling factor cancels out with each other. Okay, and in particular, because it's invariant under rescaling, there is some hope of minimizing this invariant and get a non-trivial number. All right, so that was the strategy, and maybe some example is that so at least over a smooth point. So let me just take the affine space, Cn, and if I take my valuation to be the quadrimonomial valuation that I wrote down before, and we can choose the we don't have to go to a resolution this time. So let's say I choose multiplicity alpha I on the coordinate function xi. Then let's say this is positive. Then the log discrepancy turns out to be just the sum of all the alpha i's, all the weights, and then the volume of v is 1 over the product of this alpha i's. So in particular, the normalized volume of this is the sum of alpha 1 to alpha n to the nth power divided out by the product of all the weights. Okay, so in particular, you can see this is at least n to the n by the AMGM inequality. And with equality, if and only if all the weights are equal. Okay, so in particular, this means that the valuation is a multiple of this multiplicity valuation. And if you think about the metric tangent coin, this is exactly what happens. Okay, so so if you use this valuation and write down this algebraic limit that we get, you still get a smooth point. Okay, so nothing changes. So this probably the first example that indicates the valuation that minimizes this normalized volume has some nice interpretation and has some connection to this metric tangent cone. Okay, so there are some other evidence. So for instance, I think Shirley's original observation comes from some works of material. So let me just mention that in passing. So in general, if you have a toric singularity, then they always have this Ritchie flat Taylor cone metric. And if you look at this Taylor cone metric, then there's this special vector field that's invariant, that's along the direction, and it's invariant under scaling. So on toric singularities, we have a Ritchie flat Taylor cone metric. Exists. And along this cone direction, you can write down a Rip vector field that's identified with an element of, for instance, the Lie algebra of the torus acting on this singularity. So and this Rip vector field, if you think about it that way as an element of the Lie algebra, is actually naturally identified with the valuation that minimizes this normalized volume. Okay, so maybe I should say the toric valuation that minimize the toric valuation that minimize this normalized volume function. And so a large part of this is due to Martelli, Sparks and Yeo, who basically set up some variational problem to find this grid vector field. And then Shirley observed that the function they set up is essentially this normalized volume that actually can be defined for general valuations. So in particular, extends to the non-toric setting as well. Okay, so that's a little bit of the background. And so building on this previous evidence, Shirley proposed, and then later, I think the conjecture was defined by Shirley and Chenyang Xu. So they proposed so-called the stable degeneration conjecture. That's going to give an answer to the original Donaldson-Swan's conjecture, but also at the same time give an algebraic recipe for constructing this put in quotes metric tangent cones for KLT singularities in general. Okay, so this is due to Shirley in the original formulation, but then later extended slightly by his joint work with Chenyang. Okay, so let me state what they say. So if you begin with the KLT singularity, again, and let's call this, so let's suppose it's a font, so it's the spectrum of some algebra. All right, so again, the guiding principle is that we should look at this normalized volume of valuations, find out which valuation achieves the minimum, and then write down this algebraic limit and show that it's actually very close, or in some sense even equal to the metric tangent cone of the singularity. Okay, so I'm going to break this down into several parts. So the first part, of course, is we have to show that there is actually a minimizer rather than just an infimum among all the valuations. So the first part of this conjecture is about the existence. So should exist, they have to exist valuation. that minimize this normalized volume function. Okay. Yeah, so probably you can have a sequence of valuation approaching the infimum, but there's no limit. Okay, so that's the existence part. And now, if you want to have a canonical construction, we'd better have some uniqueness of the minimizer. So the second part of their conjecture says that this V0 is unique with some caveat, because as I mentioned earlier, this normalized volume is defined so that it's invariant under rescaling the valuation. So so the best you can hope is that the minimizing valuation is unique up to rescaling. And then if I want to have this algebraic limit, okay, then I need to form this associated graded algebra by bringing down the valuation ideals and take all the graded quotients. And if I want to get an algebraic variety, one of the necessary conditions is that this associated graded algebra is finitely generated. And why do I call this the fourth part? Because the necessary condition for this valuation to be finitely generated is that it has to be quasi-monomial. So after passing to some valuation, after passing to some log resolutions, this valuation is really looking at weighted multiplicities of rational functions at a certain point. But in general, valuations can be just approximated by this kind of valuation. Okay, so I want the minimizing valuation to be quasi-monomial. So that's necessary if you want finite generation. And then finally, we want to relate this to the metric tangent cone construction. So one property of this metric tangent cone is that they have this rigid flat Taylor-Cone metric. So there is always this Yautian-Donaldson type principle that if you want some nice metric on your space, then it's equivalent to some kind of stability condition. So that's where this word stable comes from in this conjecture. So the last part is to establish some stability of the associated degeneration. So once you know this associated graded algebra is finitely generated, then you can form the spectrum of that. So that's an algebraic variety. And if you use the weights that define this quasi-monomial valuation, you can also write down some so-called Riemann vector field. I'm not going to say much what that really means in this context. Again, imagine it's some element in the Lie algebra of some automorphism group. Okay, so you can write down some Riemann vector inside some Lie algebra. And then the statement is that when you put this together, this is a K-semi-stable final cone singularity. Okay, so I want to try to write down what that means in concrete terms. But basically, so semi-stable is very close to polystable. And if it's K-polystable, then this will have a rigid flat Taylor-Cone metric. And there is also a very canonical procedure to pass from K-semi-stable to polystable object. So I'm not going to say that in detail. Okay, so basically in the original, if you want to solve the original Donaldson-Swin's conjecture, okay, so let me just write down some known results. So Gromov-Hausdorff limit, this x infinity, this 1, 3, 4, they are automatic because of this Gromov-Hausdorff limit construction. So so from this analytic result, Donaldson and Sun. So in particular, in that context, so Li Xu show that so if you assume 1, 3, and 4, then you get some part of uniqueness of this minimizing valuation among valuations that satisfy this finite generation property. Okay. So, and also you get the stability automatically. In particular, that's how they solve the original version of Donaldson-Sun's conjecture. Because this 3 automatic, and you get some uniqueness for variations that satisfies these properties. Okay, so in particular, that tells you the metric tangent cone. So this case semi-stable step is some intermediate step of the metric tangent cone construction. So in particular, they show that this intermediate step only depends on the algebraic structure, because everything just comes from analyzing this normalized volume function. And then the later work of Ziquan Zhuang show that the polystable degeneration is also uniquely determined by the algebraic structure. Okay, so this was for graph of limits. And now for general KLT singularities. The first part was proven by Harold Bloom about existence. And then the uniqueness in full generality was proved by Chenyang and myself. And then Chenyang also proved the valuation is quasi-monomial. And I should mention that in this context, all these proofs will be algebraic. Okay, so it doesn't rely on any ambient metric structure. So maybe the main theorem I can state for today, and this was proven sometime last year, is that so this associated graded algebra, if you use the valuation that minimizes the normalized volume function, is going to be finitely generated. And because I'm a little bit short of time, let me just make some very quick remark. So one remark is that there are actually very many quasi-monomial variations whose associated graded algebra is not finitely generated. So there are examples that I've discovered with Hamid Eben a couple of years ago, and then later in my joint work with Chenyang Xu, we also found some examples. So basically, there exists quasi-monomial valuation V, such that this graded algebra is not finitely generated. And the second example is a valuation on the smooth variety C3. Okay, so the affine 3 space. And it's even worse than that. So this valuation comes with weights along certain coordinates, but on some log resolution. Okay, so it's not monomial, but it becomes monomial on some log resolution. And it's worse in the sense that if you perturb the weights, then it becomes finite generated. But then if you don't perturb the weights, then it's not. Okay, so for rational weights, then it's finite generated, and for irrational weights, it's not. So there are some very subtle phenomenon. And then in this theorem, basically we find a finite generation criterion. Criterion for quasi-monomial valuations. So I don't have the time to define what I really mean, but basically, two things are equivalent. So finitely generated graded algebra. So having a finitely generated graded algebra plus the KLT property of this in this spectrum is equivalent to saying that this valuation is a so-called Collar valuation. And then for the minimizing valuation of the normalized volume, we can show it's a corner valuation. So I'll just stop here. Okay, so, but I'm happy to answer more questions about the details. Yeah, thanks.
All right, let us thank Ziquan for a very nice talk. Are there any questions? I guess we can stop the recording now and then we can go to questions.